Your reading assignments for last week included a proof template that we haven't discussed yet. So let's begin today by talking about the idea of combinatorial proofs. Combinatorial proofs are about showing that two numerical quantities are equal. And this is relying on the techniques that we learned for counting the number of lists or sets with certain properties. And the core idea is that if we have two different expressions that we can show are both describing the answer to the same counting problem, then those two expressions must be equal. This may seem a bit vague at first, but we'll go through some examples, and we'll also come back to this idea of combinatorial proof as we add more counting techniques to our repertoire over the course of the semester. In one of our recent in-class exercises, we gave an expression for the cardinality of the union of two finite sets, but we haven't actually proven that that expression is correct. We can do that with a combinatorial proof by first rearranging this equation slightly. So we've moved the cardinality of the intersection to the other side, and now we have two quantities that we want to show are counting the same thing. In this case, we could think of applying a red label to every element of A and a blue label to every element of B, and then counting the total number of labels, and we want to show that both sides of this equation count the total number of labels. One way we could count the total number of labels is the number of red labels plus the number of blue labels. And since we put a red label on everything in A and a blue on everything in B, the cardinality of A plus the cardinality of B gives us the total number of labels. On the other hand, we could count the total number of labels as the number of objects that received at least one label plus the number of objects that received a second label. And so we can add these together to count up the total labels. And therefore, these two quantities must be equal. So we would conclude our proof by writing that down. To see this example in the book, you should go back to the section 12 reading from last week, where proof template number 9 was stated. But today's reading also contains some more examples of combinatorial proofs. And now I want to go through an alternate combinatorial proof for one of those theorems. Proposition 13.1 in the textbook says that the sum of the whole number powers of 2 up through 2 to the n minus 1, which we can express in summation notation this way, is equal to 2 to the n minus 1. The book shows this proposition using a combinatorial proof involving counting sets. I'd like to show instead a combinatorial proof of this proposition that uses lists corresponding to the digits of binary numbers. The quantity that we'll be counting is how many positive integers we can represent with up to n digits in base 2, also known as binary. In our normal base 10 number system, when we write down a number like 1025, we are saying that we have 5 ones, 2 tens, no hundreds, and 1,000. So each column of the number represents a successive power of 10. We have a digit for 10 to the 0, another for 10 to the 1, then 10 squared, then 10 cubed, and so on. Because each column represents a power of 10, we refer to this number system as base 10. And so if we instead operate in binary, which is base 2, we will have a column for each successive power of 2. So we'll have a column for 2 to the 0, 2 to the 1, and so on in the case of 1025 up to 2 to the 10. And to think about this more easily, we can write down the value of each of these powers of 2 expressed in base 10 the way we're used to. And so we can express the number 1025 in base 2 by having a 1 in the 1024's column, followed by 9 zeros, and a 1 in the 1's column. If we instead wanted to express 1026, we could swap this 1 into the 2's column, and now we have a 1024 and a 2. And then if we put this 1 back, now we're representing 1027. So in base 10, we have available to us the digits 0 through 9, whereas in base 2, we have only the digits 0 and 1. But we can still express any integer uniquely in this notation. So we'd like to figure out how many positive integers can we express given n binary digits. Well, if we consider the n-digit base 10 numbers, the smallest is a 1 followed by n minus 1 zeros, and the largest is n nines. In base 2, since our only digits are 0 and 1, our range of values goes from 1 followed by some number of zeros up to 1 followed by that same number of 1s. So if we have n digits, 1 followed by a bunch of zeros is 2 to the n minus 1, and 1 followed by all 1s is 1 less than if we were to roll over to one more digit. So this would be the number 2 to the n, and so this must be the number 2 to the n minus 1. Since 2 to the n minus 1 is the largest number that we can represent with n binary digits, it's also the largest number that we can represent with up to n binary digits, and so the number of positive integers we can represent in up to n binary digits, well, we can go anywhere from 1 up to this quantity. So 2 to the n minus 1 is one way to count the number of binary numbers in up to n digits. Since the range of possible integers we can represent goes from 1 up to 2 to the n minus 1, there are 2 to the n minus 1 integers that we can represent. So this gives us the right-hand side of the equation as one way of counting the number of integers we can express in up to n binary digits. But another way that we could express this same quantity is by thinking in terms of the lists of digits. So first of all, how many positive integers can we represent with one binary digit? Well, with one digit, we can represent either 0 or 1. And since we're only interested in positive numbers, we throw out the 0, and so there's only one option. If we think about two-digit binary numbers, well, to get a two-digit number, we can't start with a 0 because that would be equivalent to one of the one-digit numbers. So we have 1, 0, and we have 1, 1. So here we had one possibility. Here we have two possibilities for 3 digits. Again, it needs to start with a 1. So we have 1, 0, 0, which is 4. Then we have 1, 0, 1 representing 5, 1, 1, 0 representing 6, and 1, 1, 1 representing 7. And so we have 4 possibilities. And so, in general, the I-digit binary numbers will start with a 1 and then be followed by I minus 1 elements that can be either 1 or 0. And so, since there are two choices for each of those I minus 1 positions in the list, we have 2 to the I minus 1 possibilities. And so this gives us another way of counting all of the integers with up to n binary digits, is that we can count all of the one-digit numbers, then the two-digit numbers, and so on up to n. And so to count all of the binary numbers with up to n digits, we can sum up for all of the lengths up to n, the number of possibilities. And so now we've shown that the left-hand side of this equation is also an expression for the number of positive integers that can be expressed with up to n binary digits. And so, since both sides of this equation are counting the same quantity, this equation must hold true. In class, we'll see some more examples of using our techniques for counting the number of sets or the number of lists with certain properties to show similar sorts of equalities. And over the course of the semester, as we learn more techniques for counting different sorts of collections, we will get more and more mileage out of this idea of a combinatorial proof.